All right, folks, we have come to one of my favorite functions. This is x to the power x. I think we looked at a limit of this function as x approaches 0 from the right on possibly the very first, within the first week of class. So we've kind of looked at this function once, and you may recognize its graph. If you take this and graph it in Desmos, it might look familiar. But this is a pretty weird function because it doesn't classify as a power function. A power function is an exponential expression where the base is x, but the power is constant, like x squared or x cubed, right? And this doesn't classify as an exponential function because an exponential function is where the base is constant and the power is a variable. So that would be like e to the x or 2 to the power x or something like that. So this is neither of those because both the base and the power are variables, and they're the same variable. It's x to the power itself. So if you attempt to apply either the power rule or the rule for taking the derivative of an exponential function, I'll just call it the exponential rule. If you attempt to apply either of those, you'll actually get the wrong answer. I'll just show you what that would look like. Attempting to do the power rule, we would bring the power down, x times, and then we reduce this power by 1. X times x to the power x minus 1, which ironically actually ends up giving you back x to the power x, because multiplying by x just adds 1 to that power and cancels out the minus 1 that you just did. But this is wrong. Okay, I'm putting it there because actually you'll see, when we do find the answer, it is extremely surprising. Okay, if we were to attempt to solve this derivative with the exponential rule, we'd say, well, the derivative of an exponential function is itself times the natural log of the base, which in this case is x. But that is also wrong. So neither of these are correct, but we got them up in the right-hand corner just because you'll see. You'll see. So what we can do to actually figure this out is something called logarithmic differentiation. So now that we've learned the derivative of the natural logarithm, we're going to use it because logarithms have all sorts of useful properties. So the main property that we're going to be using in this example is that the log of a to the power b is b times the log of a. This is the power rule for logarithms. You can take that exponent that's inside a log and sort of pull it out and make it a constant multiple outside the log. So that was something you learned back in college algebra. So what we're going to do is we're going to take the function we want to take the derivative of and write y equals x to the power x. We want to find the derivative of y with respect to x. But before we do anything, we're actually just going to do a logarithm of both sides of this equation. Okay, it turns out x to the power x is only valid for positive x values anyway, and it always gives you positive outputs, so logarithm is a valid thing to do because both sides of this equation will be positive. So when you do that, then now we can apply this rule and take this x power and bring it out and make it a multiple like that. Okay, now that we've taken advantage of that handy-dandy rule for logarithms, now we're going to do a derivative of both sides. So now we're doing implicit differentiation. On the left, we have the derivative of the natural log of y. We just learned that that is 1 over y, right? Except, remember, when we're doing implicit differentiation, it is implied that y is a function of x. So if we do any derivative that involves y, we have to treat it like a composition, which means we apply the chain rule and multiply by the derivative of y with respect to x, which is what we want to solve for anyway, so it's got to be there. So the right side is a product, x times the natural log of y. So we've got to do the product rule on that over there. So we'll do the derivative of x times the natural log of x plus x times the derivative of the natural log of x. So that's like the f prime times g plus f times g prime, product rule. All right. Now, evaluating those derivatives, we have 1 times natural log of x plus x times the derivative of natural log is 1 over x. That part, x times 1 over x, is just going to actually be 1 because these will cancel out. So now, to finish this off, we're going to take both sides of this and multiply by y, canceling the y on the left. So now we have the derivative of y with respect to x is natural log of x plus 1 times y. Except what is y equal to? Back up here, what we really started with was y equals x to the power x. So this is times x to the power x, all right? All right, now here is the kind of mind-blowing moment. Distribute this through. What do we have? It's x to the power x times the natural log of x plus x to the power x. That is the correct answer. And as you can see, it is just the two incorrect answers that we got earlier added together, which is just wonderful. So it turns out that, this is just amazing. It turns out that what is going on here, and if you're not interested in this, by the way, this what I'm about to explain is not really necessary. So you can, if you'd like, stop watching. But it turns out that what is going on here is actually can be explained, if you want to, by thinking of the base and the exponent, the base and the power, as like two different variables. You can dive into the world of multivariable calculus and think of this as like a function of x and y, and then you've got like x to the power y like that. And then it turns out that when you do this, you do a derivative of this. You do derivatives with respect to x, and you do a derivative with respect to y. It's like you have two different variables. And for the derivative with respect to x, for this part, you actually use the power rule, because you're treating y as if it's constant, right? You treat y as if it's constant. And for this part, you use the exponential rule, because you're treating x as if it's constant. And then you add these together to get the derivative, and then you let let y equal x, so that they are actually the same variable, and then you kind of do that substitution, and you end up getting this. So in a wacky turn of events, there's a way to look at this where you, even though variables are both x to the power x, if you think of them as different variables, independent of one another, then you actually do use the power rule and you do use the exponential rule, add them together, and then you make them the same again, and you end up getting the right answer. So there's a little bit of fun preview, perhaps, of what multivariable involves.